Hello again, friends. In this video we're going to be working on trying to find the volume of a shape that's created when you rotate a region around our y-axis, and we're going to be trying to find this volume using the washer method. So to get started, I have two functions written down here for us. We have x equals y squared minus 4y, and we have x equals 2y minus y squared. And this top one I have pink, and so that's this guy right here. And then the bottom one I have blue, and that's this function right here. I already got them graphed out for us, so we have a visual as to what we're working with. So we're trying to find the volume in between these two curves from y equals 0 to y equals 3. So that's up to this point right here. So everything in here. And then we need it from when x equals 0 to x equals negative 4. So x equals 0 to x equals negative 4. That means the only region we're trying to find the volume, the region we're rotating around the axis is just going to be this stuff right in here. So we're not going to be including this guy because he's not in our bounds for our x. With that in mind, we're going to have to manipulate our work here a little bit in order to remove this section from our region that we're rotating. So in order to do that, instead of just jumping right into the washer method, we have to consider breaking this up into two parts. And that's because we use the washer method when we do have like two functions and when we see that, like this top part, we have those two functions, right? So we have here the pink guy and the blue guy coming into play when we rotate it around, right? They'll both be rotated around. Down here though, underneath when y equals 2, so from 0 to 2 here, the only function that's going to be rotated around our axis, our y-axis, is just our pink function. This blue guy, he's going to be gone. So because we're only considering the pink function up to this point, we have to split this up into two parts, where the bottom part, because we have just the pink function, we use the disk method, and then the top part from 2 to 3, because we have the blue and the pink, we're going to have to use the washer method because we have those two functions in play. Okay, so with that in mind, let's break up our work. So like I said, we're going to be splitting it up, so I'm going to do the bottom half first. So the bottom half is just where we're working with our pink function, right? So we're going from 1 to 2, and we're going to 1, 2, 3, 4, and our pink function up to this point, we look something kind of like this, and he's starting to curve around up there, right? So that is just the region that we're going to be working with, just this region right in here, up to this point. And we don't want this blue guy because we're not going past when x equals 0, so this is it. That's all we're working with. So now we have to rotate that around our axis. So we're going to get a shape that looks something kind of like that. And if we're to draw this in a more like 3D model, we're going to see we're going to get a beautiful circle, and this is going to kind of taper off down here. They're going to kind of meet together, and then that's what the shape we're going to have. With our axis running through the middle. That's our shape. So with our past work, what we've done was just finding the area rather than finding the volume. If I were to ask you to find the area of just this bottom region here before we rotated it, of just this area right here, what we would have done is we would have drawn a rectangle in here and given it an infinitely small width, dy. And then we know that we have a width, so to find the area of the rectangle, we would find the length of it, right, which is defined by our function, right? So it's longer up here than it is down here. We're going to have a longer rectangle up here because the function, expands out, where down here it tapers in. So we know that our function defines the length of our rectangle. And so therefore what we would have done to find the area of this piece, we would integrate with multiplying our function by our width dy within our bounds. here we're going to do something similar, but because we have this rectangle in here with the dy, and we're rotating this region, we have to rotate our rectangle all the way around as well. So when we rotate our rectangle around, what we're going to see is that on the inside here, when our rectangle gets rotated around, it's going to create a circle in our shape. It's going to create more than a circle because, right, we said we had as a width. Because it has a width dy, it's going to be a cylinder within there. It's going to be a disc, a really thin disc. So that's why we call this the disc method. Because what we're doing is we're creating like infinitely small discs in here, and we're finding the volume of kind of each of those individual discs within our region to find the volume of our total shape. So in order to do that, we take the integral from our bounds a to b of pi r squared dy. And remember, we're in dy because we are rotating around the y-axis, and our rectangles are perpendicular to our axis. So because they're perpendicular, they have a width, a dy, right? Our width is in terms of y. So looking at this equation, what we see is it's literally the equation for the volume of a cylinder. We have a width, dy, and then we have the area of the circle, pi r squared, so that'll tell us the area of the top. So we're finding the volume of all these individual cylinders that make up this entire figure when we integrate this. That's what it's doing. So we know why this is the way, why this formula is written the way it is, but now what we have to figure out is what is the r that we have to plug in. So when we think back to what we did before, right? We said our rectangle has the length that's defined by our function. Well, the same can be said for our radius, pi r squared. Our radius is defined by our function. Down here, you're going to have a smaller radius than you would up here. Up here is going to be a larger radius, right? Our function defines the radius of all of the discs within our cone shape that we have here. So because of that, what we can do is we're going to plug in our bounds. So we're going from 0 to 2, and then pi, our radius, this is the pink function, right? So our radius, we're just going to plug in y squared minus 4y. The whole thing is squared, dy. And this equation right here, this will tell us, I'm going to erase this guy now that we have figured him out. I'm going to rewrite him up here. This equation is going to tell us our volume of this bottom half from 0 to 2. So now that we've figured out the volume for the bottom half using the disk method, we can now shift to using the washer method to figure out the volume for the top half of our function. So I'm going to erase our work that we have up to this point, and we're going to use the washer method now. So we're going to graph out what we have again. And I'm going to make him a little bit larger this time so we can actually kind of see what we're doing. So he might be a little bit out of scale in comparison with the last stuff, but just so we can see what's happening. So once again, we already figured out the volume below this point. So we're only figuring out the volume of what's left up here. And we know that we have two functions going on, right? So we have this one that kind of curves around and goes through a point, and then we have our blue function, which goes through a point kind of like that. So this is the region that we're going to be rotating, just this region in here, right? So when we rotate this around, we're going to see on the other side, he looks something kind of sort of like this. So this guy goes up, and this guy kind of curves around. So that's our shape. That's our that's the shape we're trying to find the volume of. And if we were to draw this guy out, this is probably going to look terrible, so bear with me. We're going to have this, he's going to curve around, right, on both sides. And then what we're going to see is he's going to kind of make that circular shape. And then within him, there's going to be, this is all flat, there's going to be this cone that's kind of hidden away, tucked inside. So he's kind of like this flat, round, circular crescent shape, and then inside we have this hidden cone, right? And this is kind of more so, if we're rotating this around, I'm going to draw this in a more circular way, so that way we can kind of see that this part is still being rotated around, and it just meets here at the middle in this cone. So this is all flat underneath. So this is where the axis kind of runs through. Our x-axis was right through there. And then our y-axis runs right through the middle. So kind of tricky to picture, but bear with me. So yeah, he's like kind of like a bowl, and then he has like a cone kind of in the middle of it, right? Kind of see what, like this is what they cut, if we slice it, this down the middle, that's what it's going to look like, right? So now that we kind of have a visual of what we're working with, we once again have to find the volume of this shape. And like I said before, what we did is we took a rectangle. So last time we took a rectangle from our pink function, so this is our pink function, and we drew it out all the way to our x-axis, right? And you said it has a width dy. And when we rotate this all the way around, what we're going to get again is a disk, right? So I'm going to draw us a disk. So we're going to say that this makes our disk right here. And that disk is inside of here and goes the entire way through. But we have this complete disk on the inside here, right? We don't want the whole entire shape though, do we, right? Because we're not rotating in here. This region is not included in our bounds, this region. So what we have to do is we have to subtract out the radius of, so we have a radius from our pink function to our x-axis. We have to subtract out the radius of our blue function to our x-axis. So this radius right here, we're going to have to remove. And what that does is it removes an entire disk on the inside. So this entire disk created by the blue function on the inside is going to be gone. And what that leaves us with is this washer shape, this donut shape on the inside. That is what we're going to use. Instead of using disks on the inside, we're going to use all these individual washers to determine the area of our shape. Or not the area, the volume of our shape. And the washer method, so it goes from our bounds a to b. We're going to have pi r squared from the right. We're going to subtract out pi r squared from the left, dy. And we see that what that does is it takes, we see our kind of, like before we had our disk equation, right? It takes out the disk on the middle from the total disk, the big disk, and it gives us just this washer left over. So when I say from the right and left, whenever I'm referencing in this first quadrant here. So our function furthest to the right, our radius furthest to the right, is our pink function. So we're taking the disk, like I said, created by that entire function up to this point. So from here all the way to here. And now we're going to subtract out our disk with our radius of our left function from here to here. And we know our radius, like I said, is our functions, right? Because our radius is determined throughout the shape, throughout our bounds, by our functions, right? So for our left disk, our inside disk, right, our radius is going to be smaller here and larger up here. So we're going to plug in our entire function for our left radius and our entire function for our right radius. And then our bounds, once we plug in our bounds at those specific points within our bounds, it's going to subtract our inside disk from our large disk. And that's going to give us our total volume for this upper region. So using our format for our formula, I'm going to write out our, what we have, what we're trying to find the volume of. So we're going to be integrating from 2 to 3. We're going to have pi, and our r to the right is this function right here, and that's our pink function. So we're going to have y squared minus 4y squared. And now we're going to subtract out pi. times our left function, which is our blue function. So we're going to subtract out pi times 2y minus y squared, right? Because both of these are radiuses, so they have to be squared, dy. And that is our volume. This integral tells us our volume for our entire region that is mapped when you rotate this area around our y-axis. So we have two integrals now for two regions, for the bottom half and for the top half. To find the total volume that's created by these two regions, you simply just have to add the two integrals together. So now that we have our equations, our integrals, what we're going to have to do to find our volume is we have to integrate them. So the first thing I'm going to do is I'm going to do a little simplification because our work here is a little bit messy, right? We have our radius is squared, so I'm going to FOIL all of those out, and we're going to get kind of a messier equation. We're going to simplify that, and once we get a nice simplified equation or integral, we're going to then integrate to find our volume. So, like I said, my first thing I'm going to do is I think I'm going to erase our picture here because we don't really need it anymore. So, we're going to rewrite this. We're going to integrate from 0 to 2. And what I'm going to do, I'm going to pull my pi out in front, actually, so that he's just going to kind of follow us all the way through. So we're going to integrate from 0 to 2. And we're going to have y squared minus 4y all squared. And that's going to FOIL out to be y to the fourth minus 8y cubed and plus 16y squared. Now we're going to add on our other integral. I'm going to pull my pi out of both of my pieces. So we're going to integrate from 2 to 3. And then when we FOIL this part out, we're going to get y to the fourth minus 8y cubed, plus 16y squared. And then when we FOIL this part, we're going to get negative 4y squared plus 4y cubed minus y to the fourth. So, and then all of that is going to be integrated. I forgot my dy, so with dy. So I'm going to simplify. So what we're going to get now is we're going to get our pi. We're going to go from 0 to 2. And we're going to get, this is all just going to stay the same. So y to the fourth minus 8y cubed plus 16y squared dy plus our pi times our integral from 2 to 3. And we're going to get a beautiful negative 4y cubed plus 12y squared. And that is going to be when we simplify this integral right here. So now that we have two nice simplified integrals, we're going to actually integrate our work. So when we integrate our first integral, what we're going to see is we're going to get y to the fifth, and then we're going to multiply by reciprocal 1/5 out in front. We're going to do y to the fourth, divide by 4, and so we're going to get minus 2y to the fourth. We're going to get, add 1 to our exponent here, so we're going to get y cubed plus 16 over 3 when we multiply by reciprocal. And remember, that's within our bounds, 0 to 2, and we're multiplying by pi. And then we're going to add on our pi times our other integral, so we're going to have y to the fourth, and we divide by 4, we're just going to get negative 1/4, negative 1 y to the fourth. And then we're going to add 1 to our exponent here, so that makes that a cube. When we divide 12 by 3, we just get a beautiful 4. And that's that for that integral. And we're going to be integrating, or plugging in our bounds from 2 to 3. So that is our completed work after integration. And once we plug in our bounds, we're going to see that over here we're going to get a 256 over 15 pi. And then here we're going to add on, this simplifies down once we plug into our bounds, an 11 pi, which gets us a grand total of 421 over 15 pi. So that tells us our region. So if you think back to what we had drawn for our beautiful graph, right? I'm just going to erase all of this. Goodbye. So if you think back to our graph, once again, that tells us our region. When we rotate our region, that's determined by our function here. Right, we had this going on, and then we had this going on. So when we rotate, we're not rotating this region, right? When we rotate just this area right here around our y-axis, we see that we get our beautiful volume of this when we split up our functions and use the disk method for the bottom and the washer method on top. So this problem required slightly more work than expected because, like I said, we had to recognize the fact that for part of our problem we had to use just the disk method, and for the other part we had to use the washer method. But I hope this effectively kind of demonstrates how to employ the washer method using when we rotate things around our y-axis to find volume.